In this final segment, we show the formulation of some of the recovery problems we mentioned at the beginning of the class last week. More specifically, we show the formulation of the image super resolution, video super resolution, pan sharpening, and the dual exposure problems. It should then be clear that these are indeed inverse problems, and in principle, we could use any of the techniques we covered in the last 2 weeks to provide solutions to these problems. So let's have a closer look. We will show next the formulation of these 4 recovery problems, namely image and video super resolution, pan sharpening, and the dual exposure problem. We will talk about in-painting, another one of the recovery problems I mentioned earlier in the last week of classes when we talk about sparsity. And then for some of the other recovery problems, such as the deblocking, artifact removal, we do need information that we'll start covering next week, namely image and video compression. We explain here the basic idea behind super resolution, or so-called geometric super resolution, in a somewhat idealized way. The first scenario is shown here. A single camera takes multiple pictures of the same scene. The assumption is that there is a subpixel shift between the acquired images. Each of the acquisitions is a low-resolution image. The second scenario is that multiple cameras take a picture of the same scene. The same underlying assumption holds, that is, there is a subpixel shift among the images. The third scenario is that a video camera is recording a dynamic scene. Due to the motion of the objects in the scene, their depiction in each frame is with subpixel shifts with respect to their location in a neighboring frame. So in all these 3 scenarios, low-resolution still images or video frames are acquired, as shown here. These frames are related by subpixel shifts globally, as in the first 2 scenarios, or locally due to the motion of the objects, according to the last scenario. If we show the low-resolution images on the same grid, for the first 2 cases of a global shift, then the picture shown here results. So this is a pixel shift here, while for example here this is a subpixel shift. So conceptually, each low-resolution image samples the continuous 2-dimensional scene at different points, and therefore if we estimate the subpixel shifts, we can then utilize all these observations and be able to reconstruct an image frame at a higher resolution. So this is the objective of super resolution. So the objective of super resolution is to estimate the global or local subpixel shifts and then generate a regular grid, either a still image or a video frame at a high resolution. Based on the discussion we had in the previous slide, we show here the image super resolution acquisition model or the gradation model. X is the high-res image, and Y of K, let's say Y1, Y2, Y5 are the low-resolution observed images. So according to this model, the high-resolution image is first motion warped. This could mean just subpixel shifted, or a rotation component might be present, or any affine transformation might be included in this motion warping operator, which is described by the parameter S of K. Then this motion warped high-resolution image is blurred by a system with point spread function H of K, and this blurred warped high-resolution image is finally downsampled according to this operator A to generate the low-resolution image. So all these operators can be combined into this operator here. So the problem is, given the low-resolution observations, k equals 1 to 5 for this particular image, and knowledge of B of k, S of k, we try to find an estimate of the high resolution image, given also maybe some knowledge about the noise. Now, the motion parameters need to be estimated. The blur may or may not be known, so if it's not known, then we have a blind image super resolution problem. So it's clearly an inverse problem, a recovery problem, and any of the approaches we covered so far could be potentially applied to solving this problem. One can follow a sequential approach according to which first the motion parameters are estimated, maybe followed by the blur, and then after both of them are estimated, they're utilized here to define B of k and solve this inverse problem. But maybe ideally, as was argued at an earlier point, we would like to estimate all the unknown parameters along with the high-res image simultaneously, so that errors that occur during the estimation, let's say, of the motion parameter are utilized in estimating the high-res image. We show here the acquisition model for the video super resolution problem. As you'll see, it's very similar to the acquisition model for the still image super resolution problem. So according to this, the high resolution frames denoted by X, each of them is blurred by B, downsampled by D, noise is added to generate the sequence of low resolution frames Y. So the high resolution frame X of k is blurred, downsampled, noise is added to generate the low resolution frame Y at time k. Now the high resolution frame X at time k can also generate additional low resolution observations at different time instances according to this formula. So the high resolution frame X at time k is motion compensated or motion warped and mapped to a time I, blurred, downsampled, noise is added, and the low resolution frame at time I is generated that way. So we see that one high resolution frame at time k here can generate as many low resolution frames as we would like at different time instances based on the motion field. So it's exactly the same formulation as in the previous case. The main difference is that this now C of dik, as shown here, does not refer to a global motion or global warping of the frame X of k, but instead to a local one. So we need to find the motion of the moving objects in the scene. So we need to find the motion for each and every pixel in the frame k with respect to the frame at time I, and this again motion field is going to do this mapping between the two frames. And the motion field can be just a purely translational field or also include rotation or any other transformation that it seems to be necessary to model the particular data we're working with. An interesting and more challenging video super resolution problem occurs when the observed video is now compressed. This is indeed the case with many low-end video cameras that do not make available the original data, the source data, but only a compressed version of them. I know we have not talked about video compression yet. We'll actually start doing so next week, but for the purpose of this discussion, we only need the general idea about it. The notation is different than in the previous slide, but I will not be writing any equations, just want to describe here the concept. So according to it, we start with the high resolution video here, which is acquired by a camera and based on an acquisition model like the one we described in the previous slide, this low resolution video is observed. Now this is input to a compression system, and the output of the compression system are the low resolution compressed video, but also information that is generated by the coder, the video coder. And such information is a sparse motion field, as well as information about the quantization that was used, the quantizer step sizes. So then the problem in this case is to utilize the available data, which is the compressed low-res video, but also this, you might say, auxiliary information provided by the coding scheme, motion vectors and quantizer information, and we want to obtain an estimate of these high-resolution video frames. So clearly, in addition to the acquisition system that we described in the previous slide, we also have to model the compression system, and utilizing these two models, again, we want to reverse the path and somehow from the low-res go back to the high-res data. So this is indeed an inverse recovery problem like the ones we're describing here. We discuss here the acquisition model for the punch sharpening problem, which is also a super resolution problem. So in remote sensing applications, a satellite such as Landsat is imaging part of the Earth, as shown here. Now, ideally, the sensor on the satellite would have generated these high-resolution multispectral images, which we denote by Y of B, and let's assume that we have capital B channels. But instead of generating these high-res multispectral images, a spectral decimation is taking place. So we are adding up the multispectral images this way, and a so-called panchromatic image is generated according to this model. So a panchromatic image X is the weighted sum of these high-resolution multispectral images, and we assume we have B of those, B channels, and the lambdas are obtained from the sensor spectral characteristics. In addition, a spatial decimation is taking place. So each of these multispectral images is downsampled, and here is an example, color-coded low-resolution multispectral image, and the model of this decimation is shown here. So the high-res multispectral image B is blurred and then downsampled, noise is added, and this low-res multispectral image is produced. And again, we have capital B of those. So the punch sharpening problem is to work with the available data, which are the low-res multispectral images and the panchromatic image, and obtain an estimate of the high-res multispectral images. If H is known, is a non-blind problem. If, however, H needs to be estimated, it becomes a blind punch sharpening, or as we saw, a super resolution problem. Taking high quality photographs under low lighting conditions is a major challenge. A longer exposure is required to obtain an image with low noise, but any motion of the camera causes blur. So the proposed solution is to obtain both a long and a short exposure images as shown here. So this is the long exposure and this is the short exposure image. Clearly, due to the camera shake, blur is present in the long exposure image. On the other hand, in the short exposure image, because there is not enough light, the image is noisy, although sharp, and in addition there is color loss. So the objective is to combine these two images, these two observations, and obtain an estimate of the original scene. One could work with this image, for example, and remove the noise, but the color loss is still there, or combine the two and obtain an estimate of the blur and then work with this long exposure image and remove the blur with any of the methods we covered in class so far. However, doing this simultaneously while estimating all the unknown parameters is by and large the direction to go. The acquisition process can be modeled using two coupled linear spatially invariant systems. So the model for the long exposure is shown here. Y1 the observed image, H the blurring matrix that introduces the blur to the camera shake, and X is the original image. Due to the camera movement between acquisitions, the image pair has to be registered both photometrically and geometrically. So the short exposure image Y2 involves these two lambda 1, lambda 2 parameters that are responsible for the photometric registration and the matrix or operator C that accounts for the geometric registration. Lambda 1, lambda 2, and C can be part of the problem, or they can be handled separately as a pre-processing step, in which case the observed short exposure image Y2 equals the original X plus noise. So the problem at hand in this dual exposure problem is to utilize the two observations, Y1 long exposure, Y2 short exposure, and obtain an estimate of the blur and an estimate of the original image X. In principle, the techniques we covered so far in class could be utilized to solve this particular problem. So yeah, we reached the end of week 7. I have to admit that the last 2 weeks were rather intense. Overall, however, these are not representative of the course in the sense that they're the most intense or dense 2 weeks out of the 12 weeks of the course. There is almost 4.5 hours of material during these 2 weeks, and this by itself is a mini course on image recovery. We saw that the material is rather mathematical, utilizing results from linear algebra, optimization, and stochastic processes. But as I mentioned multiple times already, do not be too concerned if for some of you not everything is crystal clear at this point. You have enough information to further study the topic and useful algorithms that you can utilize right away. The first week we covered deterministic image restoration approaches, obtaining the solution in a direct or in an iterative fashion. This week we covered stochastic restoration approaches. We derived the celebrated winner filter and also the commonly used maximum likelihood and MAP estimators. We also discussed the fully Bayesian hierarchical approach, which results in some of the state-of-the-art results. I hope you found the material interesting. I believe it will prove to be of use in a number of recovery problems, but also other applications, since we do not just discuss specific algorithms, but more general estimation frameworks. Next week, we'll start with another exciting topic, that of image and video compression. So I'll see you next week, and it's promised to be a lighter week.